Okay, we will discuss dimensional analysis and model analysis. And this is an interesting talk, and this is a research-oriented talk. And you have to know, you must have by this time known the dimensions of different physical parameters. And I think you will have the knowledge of all those fundamental physical parameters. And if that is known, everything is a smooth walk in this important chapter. And this requires a practice and learning. And if you can simultaneously write and listen, then this topic will make you comfortable. And this is a research topic, I think, and a definite problem or theory will be given. Both are logical, and you can do one can, provided each one of you knows the dimensions of each and every parameter. Of course, see what are the physical parameters and all those we will shortly learn. And this is a research-oriented topic, I said, and for model testing and for design work, design of different machinery. comparison of recognition. This research topic is used. And it deals with, I said, dimensions of some physical parameters, old and new. And this is, see, you are observing some table that has fundamental dimensions, length, mass, and time. So the dimensions, how to write dimensions, we all know. See, for example, mass, it is capital M, length, capital M, time, capital M. And the dimensions are also same. The symbols with which we represent are the same, of course. And there are, these are called fundamental dimensions. And if the physical phenomena consists of heat also, for example, then the temperature also comes into picture, and the temperature also to be considered as a. Okay, am I audible to you? Hello? Number one in B section. Okay, fundamental dimensions means MLT and type small t, and derived dimensions or secondary dimensions means the dimensions which are derived from fundamental dimensions. For example, you take, for example, velocity. It is the distance traveled per unit time. So distance is a parameter, a linear parameter or length parameter. So L by time. So L by T represents velocity. And in the dimensions, we write L into T power minus 1 or L T power minus 1. Similarly, acceleration. It is the rate of change of velocity. So velocity per unit time. So it is L by T into T power minus 1 or L into T power minus 2. So that is acceleration. And similarly, density. So density is mass per unit volume. So M by L cube or M into ML power minus 3. So these are all learned in previous preliminary classes by all of us. And I think you can recall these all things and these are utilized at a higher level in this dimension analysis. So the beauty of this dimension analysis once the dimensions of each and every parameter. Of course, in fluid mechanics, there are different physical parameters. By this time, uh, you must be knowing. For example, say specific weight, viscosity, pressure, of course, surface tension, like that, and along with these fluid mechanics fundamentals, there are a common parameter, common physical parameters. So you see the common physical parameters. Actually, in the offline classes, what I can do, I will derive all these things from your side, so that it is a practice section. It would be a practice section once you can recollect. For example, you see some derived dimensions have been drawn in this slide. So, geometric properties. Geometric property means the uh, the properties which measure linear dimension. See, the geometric properties, for example, area, length into width, or length into breadth. So, it is represented by capital A, and length is a linear parameter, and width or breadth is a linear parameter. So, L into L. So, the dimension is L square. Similarly, volume. So, volume has three dimensions: length, width, and height, like that. And it is L into L into L. So, L cube. And the quantities or parameters which are involved with time. So all of you mute your mics. Mute your mics. See, there should not be any intervention of unnecessary sounds while the lecture is going on. Okay, there are certain kinematic quantities you are observing: velocity, angular velocity, acceleration, angular acceleration, discharge. Discharge is flow per unit time, or volume of flow per unit time. Unit time. So that is why the discharge comes into kinematic parameter. And of course, acceleration, kinematic viscosity. Kinematic viscosity, we uh, we learned this kinematic viscosity in the first unit. So it is mu by rho, dynamic viscosity by the density of the fluid. So the dynamic viscosity is Newton second per meter square by density kg per meter. And what is the dimension of force here? I will put a question here, because to derive or to have the secondary or derived dimensions, we must be knowing the fundamental things. That's why I recall force, that is for which the unit is Newton. So, what is the dimension of force? Quickly respond. Quickly respond. What is the dimension of force? Or
M T power minus 2.
M?
ML T power minus 2.
ML T power minus 2. So how will you actually derive? How will you actually write this? How will you actually write this?
kg into meter per second square, sir.
kg meter per second square. Very good, very good. So okay, how will you derive this kg meter per second square?
Mass into acceleration.
No? What you said is correct. So you will derive this kg meter per second square from the fundamental equation for force, as you said, F is equal to me, F is equal to me, or W equal to mg. W is also a force unit, will have force unit. So with F is equal to ma, so mass into acceleration. So mass capital M, acceleration L into T power minus 2. So acceleration is also a derived parameter. So which is rate of change of velocity, dv by dt, like that. So v by t. So velocity is also a derived dimension. So it is distance traveled unit time. So in that way, the acceleration will have L into T power minus 2, the dimension of L into T power minus 2. So M into L into T power minus 2. In that way, so why I'm asking here, for example, I told you kinematic viscosity to derive the unit of the dimension of kinematic viscosity, which is defined as mu by rho, mu equal to mu by rho, where mu okay, how will you, for example, if you cannot recall the units of dynamic viscosity, for example, then how will you recollect? How will one can recollect the dimension of a certain parameter? For example, here, that certain parameter is dynamic viscosity. If suppose, if you by mistake, if you don't remember or don't recall the dimension of, for example, viscosity or dynamic viscosity, how will you actually recollect? So,
Shear
okay,
stress by velocity gradient.
okay, please repeat.
Shear stress by velocity gradient, sir.
Very good, very good, very good. Okay. Instead, you can write the Newton's law of shear stress. Okay, what you are telling is correct. Tau equal to how will you write tau? Shear stress is equal to mu dou u by dou y. So velocity gradient. So in that way, mu equal to tau by dou u by dou, where tau is shear stress and dou u by dou is velocity gradient. And we know shear stress equation are, how will you write shear stress dimension? If you, for example, if you cannot write directly, indirectly you can write, that is derived. So shear stress means force per unit area. So force by area. So for force, as you said, mlt power minus 2, you can write, divide by area, L square, and divide by that tau is over dou u by dou y. So the velocity will have the dimension of L into T power minus 1. And dou u, or difference in velocity will have the same dimension, L into T power minus 1. And dou u by dou y. Why? What is the unit of dou y or dy? It is L, linear
Meters.
dimension, length. So in that way, the velocity gradient will have a dimension of T power minus 1. Velocity gradient will have the dimension of T power minus 1. In that way, actually, this is to be practiced, right? This is to be practiced instead of uh, uh, listening and looking at the slides. This is to be practiced in the sense, once, for example, I asked here at kinematic viscosity, we structured and we had a doubt. We raised a doubt to how one can recall the units of kinematic viscosity. So if you write the secondary dimension or derived dimension kinematic viscosity like by the equation mu equal to mu by rho, and write derive the dimension of mu, as you said, tau equal to mu dou u by dou, or shear stress by velocity gradient. Then you can derive the units of mu, and then you can derive the unit of kinematic viscosity, and ultimately you will get the kinematic viscosity meter square per second, and it is L square T4 minus 1. So that's why this chapter, if I tell something about units, if I tell or derive the final dimension of a certain physical parameter like this, it is of no use to you at all. But what you require is simultaneous practice in the classrooms. What I do in general, uh, I test the students by just writing a number of physical parameters like on the board, and then test to derive the dimensions. And what I do for a beginner, because this is the beginning, what I do in general, I give a very well-known physical parameters to you, and test it later. A little bit derived, little bit parameters which require little bit derived. For example, as you said, mu equal to shear stress by velocity gradient, tau by dou u by dou. So if in that way, one can uh, derive the dimensions of each and every physical parameter. But see, it's not easy unless a few concepts are inbuilt in us. A few concepts are uh, in our mind. That means some you said f is equal to ma, and you said tau equal to you said mu equal to shear stress by velocity gradient. Like that, those are the concepts which are required to derive these secondary dimensions. So in this slide, all the parameters which are uh, shown in a color table are all secondary dimensions or derived dimensions. So see the difference. See in the 2 marks questions are uh, fundamental bit questions in the examinations. You will be asked like this: what do you mean by fundamental dimension and secondary dimensions or derived dimensions? See, a fundamental dimension is the one which has only see MLT M, a capital M is a fundamental dimension. Mass L, length, is a fundamental dimension. Time T, capital T, is a fundamental dimension. And if any heat is involved in a physical phenomenon, of course, we restrict mechanics problems up to some heat. If it is that much common, but in some physical phenomena related to fluid mechanics, if heat is also involved, so then time comes into picture, which you can represent by either small t or theta, whichever you want to represent. It is not unique. There is no unique rule to represent these things. So in that way, we will have either 3 or 4 fundamental dimensions in fluid mechanics problems. And of course, if we extend our discussion of writing derived dimensions, all the derived dimensions whatever what are studied and whatever are there, it's a huge subject. For example, you may deal with current voltage like that, but they are all not required in fluid mechanics. They are all not at all required in fluid mechanics. We restrict ourselves to MLT, and uh, if it is uh, required type, if it is required temperature. So maximum four parameters we require, but normally in most of the fluid mechanics problems, only three fundamental dimensions would be there. And now the dynamic quantities have been shown uh, under the serial number D. So the dynamic quantities are related to inertia, mass. So force, as you said, how can we derive force? F is equal to me. So the dimension of mass is A, acceleration, L into T power minus. Then wait, how will you derive? W equal to mg. So capital M, G, again acceleration. It will have same dimension as acceleration, L into T power minus 2. And density, rho, mass per unit volume. So mass by volume, or M by LQ. So the dimension is M into L power minus 3. So, and specific weight. Well, how will you how will you write the specific weight dimension? What do you mean by specific weight? So the such type of concepts are to be known beforehand to write the dimensions of parameters. Why all these are listed here in the problems which we will see later in this dimension analysis. They deal most of the parameters listed here, and therefore these are tabulated instead at the very beginning. These are tabulated. So this having this knowledge, one can smoothly do a problem. I am telling a problem many times because doing a problem in this unit is a smooth task. One can do any problem related to a research oriented problem or related to an experiment. We can do problem using these a sum of the parameters listed here. Okay, specific weight. What do you mean by specific weight? What is the dimension of specific weight? How will you derive the dimension of specific weight? So specific weight is weight per unit volume. So weight W has the dimension MLT for minus 2 and divided by volume LQ. So it means it then becomes MLT power minus 2 by LQ. So it becomes ML power minus 2 T power minus 2. L power minus 2 T power minus 2. So L by L cube is L power minus 2 or 1 by L square. So ML to L power minus 2 T power minus 2. And dynamic viscosity. So as I said, dynamic viscosity, you can recall from the Newton's law of shear stress, tau equal to mu dou u by dou y or mu dou u by dou y. And the dynamic viscosity, you can write mu equal to shear stress tau by dou u by dou y. See, the shear stress is force by area. In that way, if you write everything in the definition of mu, which is tau by dou u by dou y, and dou u, difference in velocity, whether it is velocity or difference in velocity, it will have the same unit or same dimension, LT power minus 1, and dou y. So it is either it is the difference in y or y, it has the same linear dimension L. So in the denominator of mu, which is dou u by dou y, we write it as LT power minus 1 by L. So it is T power minus 1. And the shear stress. Shear stress. What? How will you see? Shear stress is also given in the listed parameters. So shear stress is force by area. So it is mLT power minus 2 by L square area. So mL power minus 1 T power minus 2. That is about shear stress. Now this shear stress by T power minus 1. So it becomes mL power uh, minus 1 and T power minus 1. So 1 T power minus 2 plus 1, which becomes T power minus 1, mL power minus 1, T power minus 1. So in that way, the dynamic viscosity can be derived. And the remaining, see, uh, pressure will have the same unit as shear stress. So pressure is force by area, and force has unit of dimension of mLT power minus 2 by area L square. So it becomes mL power minus 1 T power minus 2. And you see modulus of elasticity. Modulus of elasticity will have the same unit of shear stress. So the modulus of elasticity will have the same unit as shear stress, and therefore it has dimension of mL power minus 1 T power minus 2. And now surface tension. How is the surface tension defined in fluid mechanics? It is the force acting on surface for unit length of surface. So force by the length. So in mLT power minus 2, L will cancel when we write force by length. It is the force, tensile force acting on surface for unit length of surface. So MT power minus 2. So in that way, the dimensions are to be derived from concepts or derived from the fundamental equations of that parameter. And shear stress, it will have the same unit of force by area, and we derived it ml power minus 1 t power minus 2. And energy or work. What do you mean by work or energy? What is the equation for work or energy? Work, or what is the unit of work or energy? Both have same. So force acting through a distance, some distance. So if a certain force is acting for some distance L, we write work done equal to force into length. For example, in bending moment diagrams, moment will also have the same unit as work or energy. So see, work or energy mLT power minus 2 and one more L. So it is mL square T power minus 2. Now you see the moment is not given. In this moment, you can write the same unit, same dimension for moment also, not momentum. Moment is different, momentum is different. What do you mean by moment? Moment, the moment of a force about a certain point. So force multiplied by the distance of that point from the point of action of this force. So in that way, the moment will also have the same unit as work or energy, which is Newton meter. All these have the common unit as Newton meter. So joule, which is called joule also. And what do you mean by power? How will you define power? And later, if you can define power or a certain parameter, physical parameter, or the concept equation related to that parameter, we can definitely derive the dimension. What do you mean by power? just you need not actually concisely recall what are required here, power, or at least what is the unit of power. In SI system of units, you better write power is rate of doing work, rate of doing work. So it is Newton meter per second. Work by time, rate of doing work, dW by dt, like power. So rate of doing work is power. So work has one by one you have to derive. It has derive. Uh, you will get the power unit or dimension ml square t power minus. How all these things you have to practice. Power. It has the unit of Newton meter per second. Newton is a force unit, ml t power minus 2, and one more meter is there, ml square t power minus 2, and by t is there, ml square t power minus 3. Like that, ml square t power minus 3 is the dimension of power. And then torque. Torque. How will you define torque? Torque and moment and work and energy, these all have the same unit, which is Newton meter. And therefore, we derived already, um, we have derived for work or energy and momentum. Moment, the dimension is ml square t power minus 2. And momentum, what do you mean by momentum? What is the fundamental equation related to momentum? Moment is different and momentum is. What is the fundamental equation for momentum? Momentum.
Mass into velocity, sir.
Mass into velocity, mv, that's all. So mass into velocity. So therefore, we write mass capital M, velocity L t power minus 1. So in that way, we have to write the dimensions of different parameters which are listed and which are not listed in the table also. From very fundamental equations like F is equal to ma, W is equal to m, tau equal to mu rho equal to density rho equal to mass by volume, and specific weight small w equal to the capital W by volume, weight 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 by volume, and weight and force will have the same unit, and thrust. These are all the names which will have the same unit, Newton. And remember, tension, tensile force, tension it has the same unit, Newton. Like that, all the parameters which are listed and which are not listed have to be uh, recollected as and when a problem is involved with these parameters. And see, torque. What is the equation of torque? Force into radius. Force into radius, F into R. And in that way, we will remember momentum. As you said, the momentum will have the same the unit, the equation mv. So mass into velocity, and like that, the fundamental definition or fundamental equation related to that parameter has to be uh, recalled. Why these are to be recalled? See, nobody is perfect, and I suggest you strongly not to remember any dimension of these derived parameters, because these derived parameters are secondary parameters, are to be derived from concepts, but it does not mean that you have to remember the dimensions. It is not it is a dangerous task if you remember. So therefore, it is not recommended. I highly suggest you, and I highly insist you to not remember this type of dimensions. There are so many dimensions involved in a physical parameter. So that's so many dimensions are not to be remembered, are not to be kept in mind, but they are to be derived as and when required. And now you see the a simple problem of experimental type, which uh, which we had conducted this in intermediate or which we know in our previous studies. So here the problem is determine the dimensions of the quantities given below. Of course, the angular velocity, it is angle covered in radians per unit time. Angular velocity. Angle covered in radians has no unit. It has no unit by time, 1/2. So t power minus. And the angular acceleration, it is angular velocity per unit time. Again t power minus 1 by t. Again, it is t power minus 2. Our angular velocity will have the unit radian per second. Radian. The dimension of radian is no unit, no dimension. It is uh, angle covered in radians. Uh, and per unit time, it is called velocity. And this angular velocity, change of angular velocity, rate of change of angular velocity is angular acceleration, which is radian per second, which is radian per second square, or t power minus 2. And discharge and now you see the discharge explanation here. Instead of what I told, other than in other way it was given. What I told just now, discharge is flow per unit time, I told you. So instead of that, if you can recall the continuity equation, Q equal to AV, area into velocity, that is sufficient. So either the equation is to be recollected, or the definition has to be recollected. So here the equation is used for the charge, which is area into velocity. So area L square, velocity L by T. So the ultimately you will get L cube T power minus 1. See the kinematic viscosity, how it is derived. It is uh, derived by writing mu by rho, as we discussed, and mu is given by, as you said, shear stress by uh, velocity gradient, and shear stress is completely expanded force by area, and velocity gradient is written one by one, dou u, L by dou u is L by velocity dimension, and 1 by y, it is 1 by L. So it is L. Dy is L. So therefore, in the place of dy, you write L. So you should be very careful, or you write instead tau into dy by du. So tau, force by area, into dy is L by du is L by. Like that, you have to be careful while substituting the dimensions. And then if you expand still see step by step, this will lead to see this mass into acceleration. Force again, force has been written, mass into acceleration. So See, the problem is solved in a more fundamental manner. So in that way only, each and every problem has to be solved. Force, mass into acceleration, and the remaining parameters are written: area and time remains. So into time. So, but I always tell you not to follow any of the methods in the textbook as well as in any material given to you. Instead, once the logic, that is, once the methodology is understood by you, then you follow your own method other than that is or the own sequence other than that is given the material or textbook. So that is highly required, and because just mugging and copying down from the textbook and by heart, all these are unnecessary in the entire subject fluid mechanics, and therefore you avoid such type of things. But because for the sake of explanation, we have to uh, look into those only. But when if I ask some question, if you respond quickly, it's a different matter. If you don't respond, time will be wasted. Therefore, I prefer uh, the methodology given in this material, and therefore mass into acceleration. So mass m, acceleration L by t power L by t square, and divided by area. Area force in the force force by area is there L square, and when dou u by dou y is expanded, you will get L by t uh, by L. So L by t by L. So only 1 by t remains. So if you write like that and do the algebra as your own, that is what remains uh, in the ultimate equation you write. So here m into L is written and t square is kept in the denominator, and L square is kept as it is, and 1 by t is written as it is. So now the powers of these fundamental dimensions are to be carefully written. So m, only one m is there, so m power 1. So L, there are two L's, L power 1 and divided by L square is there, L power 1 minus 2. So it becomes L power minus 1. And there are two time terms. So when all the t's are kept in the numerator, it becomes t power 1 minus 2. So it will be t power minus 1. So ultimately, the dynamic viscosity will have ml power minus 1, t power minus 1. Now, density. For density, you are specified and dynamic viscosity. It is asked. So here, kinematic viscosity is also asked to derive. So for that, we require density, mass by volume. So mass by m by L cube, m into L power minus 3. Now, using the dimensions of dynamic viscosity or viscosity, uh, uh, viscosity, we have ml power minus 1, t power minus 1 mu divided by rho ml power minus 3. So here m gets cancelled, or m will have no power, zero power. So L will have L power minus 1 plus 3, it is L square, and t power minus 1 remains. So in that way, kinematic viscosity will have the dimension L square t power minus 1. And then force will have from MA, we discussed MLT power minus 2, specific weight weight by volume or force by volume. If mlt power minus 2 is divided by L cube, we will get the specific weight. And in that way, we have to derive the dimensions of each and every parameter. Okay, we will continue later.